Okay, I wanted to hit the high points for you of the remaining part of chapter 5 I wanted to get to. Not going to do the whole chapter. There's a section right at the end about the so-called phase rule. I don't really want to do that. And elasticity. Not super interested in those. But let's talk about what we do have. So quick, what I call a super summary of section 5.4. The dependence of Gibbs energy on temperature and pressure. So from the fundamental equation for dg, remember one of those four equations, if you apply constant pressure, you get equation 513. We said that Gibbs energy, because of this equation, surely goes down as temperatures increase because absolute entropies are always positive. The language I kind of used in class is to say as the temperature is increased, you're increasing disorder, the energy ends up being less useful. It ends up not being able to do much. Even though the energy is present, it's in a very disordered state. In order to determine absolute change for a finite process, let's say you wanted to know how much delta G changed over a certain range of temperature, you use the so-called Gibbs-Helmholtz equation on page 186. It was derived, but it's kind of this odd partial of a partial. It's useful because eventually it will lead us to be able to control equilibria. It could allow us to know the conditions to shift equilibria to one way or the other. The other dependence we investigated was Gibbs energy's dependence on pressure. That's equal to volume. If it's molar, then you get molar volume. For an ideal gas, there's a brief equation where you have, if you know P2 and P1, or you could identify P1 as a standard and write it this way. For condensed phases, the delta G is VdP, which ends up not usually being a very large. Okay, so where do we go from here? Well, in this section, we're going to explore how the Gibbs energy is involved in phase equilibria and phase changes. We kind of alluded to that in class. So remember, though, we're just going to stick with one component. So like, let's say an ice cube that's in water. If the water's 32 degrees and there's no additional heat or removal of heat, you could say that the Gibbs energy of the solid is equal to the Gibbs energy of the liquid. We know that there's a drive to things happening spontaneously toward lower Gibbs energy. But if the ice cube is just sitting in the water and it's not growing or melting, then the molar Gibbs energies are equal. You have to say molar Gibbs energy because if you threw an ice cube in an ocean of liquid water, the liquid water have way more just Gibbs energy. And on a per mole basis, that's what's equivalent here. You want to keep it as an intensive property. You don't want the properties to matter on how much you have. So if you change the conditions in some way so that the Gibbs energy of the solid was increased, how do you increase Gibbs energy? You could increase pressure, you could lower temperature. Well, then some solid would melt. That makes sense. I mean, you didn't need to take physical chemistry to know that, but this is basically what's going on with the equations. If the molar Gibbs energy of the solid is increased, then that becomes a negative value, and the reaction will spontaneously melt. You'd spontaneously go from a solid to a liquid. On the other hand, if the liquid had a greater Gibbs energy, you could make the solid a lower Gibbs energy, now that would be the reverse, right? You'd be decreasing pressure, increasing temperature, then some of the liquid would freeze. The favored phase is the one with the smaller molar Gibbs energy. So in molar quantities, we have this partial derivative is equal to this term. Because entropy of a substance is always positive, if you plot the change in G with respect to T in a fixed way or a finite way, then you're going to get a line with a negative slope. And I realize that this may seem crazy, but if you zoom forward 2 minutes, you'll get to that slide, and then you're coming back to this one. How does an increase in pressure affect phase equilibria? Well, that's what this partial is about. Equation 5.16 showed that an increase in pressure always increases the Gibbs energy, and that for vapor, the increase is the greatest because molar volumes are normally 1,000 times greater than liquids or solids. So that's why this separation is so large. So large. Because the mole volume is so large. Figure 5.3, which is the one that's on the plot here, shows how the increase in pressure in the value of the molar Gibbs energy for all three phases reflect important changes. All of the Gibbs energies increase regardless of the phase. Both the temperature freezing, the temperature and boiling shift to higher values. The shift is greater, though, in the boiling point because of the larger change in the vapor Gibbs energy. The V bar is larger for gases. The reverse also holds true. This is all based on molar volumes being larger for the liquid than the solid. Obviously, that's not true for water. Let me remind you that. So the molar volume of the solid is going to be greater than the molar volume of the liquid. That's not true for normal things. Okay, discussed that already. One thing I kind of found in here, I just wanted to tell you, I guess I knew this and probably forget it. I know students have asked me before, technically, what's the difference between a gas and a vapor? How do you know which term to use? Well, a gas is a substance that is normally in the gaseous state at ordinary temperature and pressure. So ordinary state at, let's say, room temperature and pressure. So you talk about hydrogen or oxygen as a gas at ordinary state, ordinary temperature and pressure. Whereas a vapor is something that's a liquid or a solid under normal conditions. So maybe that's something you knew, but I relearned it, and that's always nice to do. Then you feel like you accomplished something that day. So you talk about water vapor, for example. All right, so what do we have here? So as we said on the previous slide, you've got the negative slope if you plot the change in Gibbs free energy on a molar basis is minus the molar entropy. Now, why did these slopes differ? Well, I wrote this out on the top, right? If the disorder of the solid is less than the disorder of a liquid, which is less than the disorder of a vapor, you're going to see differences in the slopes because that's what dg over dt is. It's essentially the slope of these plots. And the vapor disorder is the greatest, so it's going to have the greatest numerical slope. How does an increase in pressure affect phase equilibria? Oh, by the way, I kind of jumped that. As we mentioned in class the other day, the reason the phase changes at a particular temperature is because one of the phases becomes the lower Gibbs energy, the lower molar Gibbs energy. How does increasing pressure affect? Well, I'm going to go to the other slide now. So now we have a short section on something that's called the Clausius-Clapeyron equation. So we shall derive some useful relations. Let's see if I get this here. Consider two phases in equilibria, alpha and beta. You could think of them as liquid and solid, or liquid and a gas, at constant temperature and pressure. Small changes to one will equate small changes to the other as long as they're in equilibria. So I have what I call old friend alert. That's one of my friends runs a baseball blog whenever we're playing another team that has one of our former players on it. Our old friend alert is the fundamental equation for dg. So let's apply our phase equilibria to that. In other words, what we're going to say is, again, as long as these terms are in equilibria, we could make this equality, right? The VdP minus SDT for the alpha side is equal to the VdP SDT for the beta side. Again, alpha and beta represent two different phases. Now, in the next step, what we're doing is we're rearranging the equation a bit to get something interesting. What we could show is that for the alpha to beta transition, so again, the delta is final minus initial. So imagine that this is melting, let's say. If solid is going to liquid, then the liquid is the beta and the solid is the alpha. So the difference in the molar entropy divided by the difference in the molar volume is equal to this partial. It's the dP by dt. Now you might recall that at equilibrium, we defined this when we defined what entropy was back in the entropy chapter. So if you swap in delta H bar over T for delta S, you generate this equation. It's called the Clapeyron equation. What do I have here? So remember delta S for phase changes. This guy gives the ratio of changes in pressure to changes in temperature in terms of readily measurable quantities, where delta H could be delta H of fusion, delta H of vaporization, delta H of sublimation. So for any phase change, you can get values here. So we'll see a plot in a minute. It can be expressed in a more convenient form for vaporization and sublimation by getting rid of the condensed phase, right? If a gas phase is one of the components in your phase change, the molar volume of the gas is so much larger you could approximate it that way. And assuming ideal gas behavior, you get this version down here. Did I write that correctly? dP over P? So, right, there is a rearrangement here with the P from here and the dt there. So that's how we got this version, this 5.20 version. All right. Now this is what's called the Clausius-Clapeyron equation. Clausius-Clapeyron. And so, let's see, if we want to get rid of the partials, we'll go to the next. And integrate between P1, T1 and P2, T2. So look what we have here. We have the ability to find the delta H of vaporization simply by plotting the partial pressure, vapor pressure of your vapor with respect to temperature. Assuming that the delta H of vaporization is independent of temperature. We'll kind of get back to that later. So we assume that, vapor, if we had carried out an indefinite integral, an integral without limits, we would express the natural log of P as a function of temperature as follows. That's 522. Thus, a plot of natural log of P versus 1 over T gives a straight line whose slope is, which is negative, is equal to minus the heat of vaporization, or enthalpy of vaporization, divided by R. I think that's an equation that you may have seen in general chemistry. Now, this is a surprise once we introduce it, but essentially what we're doing here, folks, is we're finding out how to draw the lines in a phase diagram. These are the slopes of the lines in a phase diagram. It's related. Look at a normal phase diagram. You're plotting pressure versus temperature. So this one has the natural log, but in the Clapeyron equation, we had dP over dt, right? So when you get that slope, that's essentially the slope of one of these lines that separates the phases. So whenever you're along a line, the two phases can coexist. Now, the line is, if the line ends up being pretty straight, it means that the delta H assumption is relatively good. And let's look at this example, 5.5, straight out of the book. Calculate the slope of the solid liquid curve. So that's the steep one there at around 273 degrees, given the information. So back to the Clapeyron equation, we want dP by dt. We want the delta H of fusion divided by the temperature times the difference between the molar volumes of fusion. So that's going to be, so fusion is solid going to liquid, so we want to have the liquid is the final. So the 0.0180 minus the 0.019, that's going to be a negative number, which is going to end up giving you the negative slope that we predicted. So it's negative 136 atms per K. It says, because the molar volume of liquid is smaller than ice, the slope is negative. We already said that. An interesting result is obtained by calculating the quantity which gives the change in melting point as a function of temperature. We find that dt by dP, the inverse, I guess, is minus 7 times 10 to the minus third, which means that the melting of ice decreases by 7 times 10 to the minus third K whenever the pressure increases by 1 atmosphere. Now, it mentions here about making ice skating possible. As you read in that paper, which I need to grade, there's more complex things going on than pressure changes. So it's a big fat lie. Example 5.6 gives you a table of vapor pressures versus temperature. And if you plot the natural log of P versus 1 over T, the slope is equal to delta H of vaporization over R. That's what the slope is. So if you take that and you multiply by R, you can get the delta H of vaporization. And you get 42.3 kilojoules per mole. The comment here is that the measured delta H of vaporization at 100 degrees is 40.79, which ends up telling you that over the range, this was over a range. I'm not sure why the book said 20 degrees to 80 degrees. The data that I'm looking at goes from 20 to 70 degrees. The point of that is that this calculated value of delta H is awful close to the measured value that's on 100 degrees Celsius. So over that range, the fact that delta H of vaporization is roughly the same. Different phase diagrams have different shapes depending on the differences in their molar volumes. We said that a little earlier, right? We ended up having a negative line between solid and liquid in the water plot because the molar volume of the solid was larger than the liquid. That's why ice floats on water. But for carbon dioxide and many, many other liquids, the solid liquid line is going to have a positive slope, and it comes down to the term that I mentioned, the molar volume. Note, for CO2, liquid is not stable below 5 atmospheres. Dry ice sublimes at room temperature and pressure. Liquid CO2 at room temperature needs to be kept at 67 atmospheres. So that's another interesting tidbit. All right, so hopefully you got a chance to watch this, and I'll answer any questions on Friday, and I'm going to prepare by doing some problems, which I haven't got to yet. All right, bye-bye.